Third objective, moment of a force. Introductory experience. If we consider a disk that can rotate freely around a horizontal axis passing through its center, and we can hang masses at different points on the disk. If we observe this figure, we represent a disk, its center O, and the axis of rotation passing through O, and the axis of rotation is perpendicular to the plane of the disk. And these different points marked on the disk, at this point we can hang different masses. In first situation, if we hang two masses M1 and M2 equal to each other, equal for example to 200 grams, such that their points of application are horizontally collinear with the axis of rotation and that they are at an equal distance from this axis. So M1 is placed at this position and M2 at this position, where the distance between M1 and the axis of rotation is equal to the distance between M2 and this axis of rotation. If we place the two masses as shown in this figure and we release the disk, it remains at rest. So in this case the disk does not rotate, so it is in rotational equilibrium. So the disk remains at rest. In second situation, let's move M2 to the right. So we displace M2 from its initial position to the right and it is placed at this point. If we release the disk, we notice that it starts to rotate in the negative direction. Negative direction, why? Since if we consider the trigonometric direction as positive, so the negative direction is the same direction of clockwise and the positive direction is anti-clockwise direction. So if we displace M2 from its initial position to this position, we show that when the disk is released, it rotates in the negative direction as shown in this figure. Situation 3. Let's move M2 to the left. So this is the initial position of M2. Now if we move M2 to the left and it is placed at this position, and if we release the disk, it starts to rotate in positive direction or anti-clockwise direction. Situation 4. If we displace M2 vertically downward with respect to its initial position. So that is the initial position of M2. Now we displace M2 vertically downward from this position to this position. And if we release the disk, we show that it remains at rest. And also in this case, similar to situation 1, the disk is in a rotational equilibrium or the disk does not rotate. Situation 5. If we replace M2 by another mass M'2 equal 300 grams. So in this case M'2 has a mass greater than the mass of M1 and M'2 is placed in initial position of the mass M2. If we release the disk, we show that it rotates in negative direction. Summary. Experience has shown that the rotational effect of a force, and in our experiment the force is the weight in this case. So this experience have shown that the rotational effect of a force on a body depends on the magnitude of force and the distance from the line of action of the force to the axis of rotation. So, the rotational effect of a force depends on two factors: the magnitude of the force and the distance separating the line of action of the force and the axis of rotation delta. If we return to our situations, so in situation 1, the two masses are equal and are located at the same distance or at equal distance from the axis of rotation. So the weight relative to M1 and the weight relative to M2 are equal. And in this case, the disk undergoes the action of two forces, W1, so weight relative to M1, and W2, the weight relative to M2. But the two forces are equal, and in this case, the disk does not rotate, so it is in rotational equilibrium. And in this case, the magnitude of two forces are equal, and the distance between the axis of rotation and the line of action of two forces, also the distances are equal. So in this case, the disk remains at rest, so does not rotate. In second situation, when we displace M2 from its initial position to this position, in fact, we increase the distance between the weight of M2 and the axis of rotation delta. In this case, the disk rotates. In situation 3, the distance, or when we displace the solid M2 from its initial position to this position, in fact, we decrease the distance. So in this case, the disk also rotates, but in opposite direction to that shown or observed in situation 2. So when the distance increases, the disk rotates in this direction. But when the distance decreases, the disk rotates in this direction that is opposite to the direction represented in situation 2. And in situation 4, when we displace vertically the solid M2 from its initial position, we find that the disk in this case remains at rest and does not rotate. And finally, in situation 5, when we replace the solid M2 by another of mass M prime 2 greater than M2, we find that the disk rotates in this direction. So in all situations, or from all situations, we can deduce that two factors act on the rotational effect of a force: the distance between the line of action of the force and the axis of rotation, and the magnitude of the force. Since when we replace M2 by M prime 2, in fact, we increases in this situation the magnitude of the force. In situation 1, 2, 3, and 4, we act on the distance. But in situation 5, we act on the magnitude of the force. And we find that if we act on the force, on the magnitude, or we act on the distance, in two cases, the variation in distance or in magnitude can make a change in rotational state of the disk. So we can deduce that the rotational effect of a force on a body depends on the magnitude of the force and the distance separating the line of action of the force to the axis of rotation. Now, the lever arm. Definition. we call lever arm A of a force F with respect to an axis of rotation delta the distance between the line of action of F and the axis of rotation. But this distance represented by A should be perpendicular to the line of action of the force, and the SI unit of the distance A or of the lever arm is meter. In these examples, we show many situations and the lever arm in each situation. In first situation, if we consider the force F, this is its line of action, and the axis of rotation delta is perpendicular to the plane of the disk and passing through its center O. By definition, if we are to if we have to determine the lever arm A, we trace the perpendicular starting from the axis of rotation to the line of action of the force F. This segment represented or by the red color represent the lever arm or the distance A needed. And in this figure, this is the distance A, so it is the perpendicular drawing from or issued from the axis of rotation to the line of action of the force, and in this case also the lever arm is the perpendicular issued from O, so issued from the axis of rotation to the line of action of the force. In this case, we noted that if we have a force F, that its line of action cuts the axis of rotation, so the distance between the line of action and the axis of rotation is equal to 0, so lever arm A is null. Now, how we calculate the moment of a force? Knowing that the moment of a force is the rotational effect of this force. So the moment of a force represents the rotational effect of the force. By definition, we call moment of a force F with respect to an axis of rotation delta the product of the magnitude F of the force and its lever arm A, and the distance separating the axis of rotation and the line of action of the force. The symbol of moment of force is denoted by M capital letter with respect to axis delta, and M is equal to the product between the magnitude of the force and the distance A, and this equation shows that the moment of the force can be positive or negative, so it has a sign. In SI unit, F is in Newton, and A, it is a distance, so it is in meter. So finally, the moment of the force has a SI unit newtons times meter. Sign of moment of rotation or sign of moment of a force. By definition, if a force causes rotation of an object in positive trigonometric direction, so in anti-clockwise direction, its moment is positive and denoted by plus F times A or simply F times A. And if the force causes rotation of an object in negative trigonometric direction, so in clockwise direction, its moment is negative, and its moment will be written as M equal minus F times A. Consider this figure where we represent two forces, F1 blue color and F2 green color. This is the line of action of F1, and this is the lever arm or the distance relative to F1 and A2 the distance relative to F2. A1 is the perpendicular issued from the axis of rotation to the line of action of the force, and A2 is the perpendicular issued from the axis of rotation to the line of action of the force F2. So if we are to calculate, or if we are going to calculate the moment of force F1 and F2, in first situation, if we consider F1 only acting on the disk, so in this at this instant we neglect the presence of F2, and if we consider F1, when we apply F1 on the disk, we show that the disk rotates in this direction. So after applying F1 on the disk, we show that the disk rotates in clockwise direction, so in negative direction. So the moment of F1 should be negative and equal minus F1 times A1. Now if we consider F2 only acting on the disk and we neglect the presence of F1, when we apply F2 on the disk, we notice that the disk rotates in this direction, so in anti-clockwise direction or in positive trigonometric direction, and the moment of the force F2 can written as plus F2 times A2, since F2 in this case has a positive moment. Note: any force having a line of action passing through the axis of rotation, for example, as this figure, the line of action of force F passes through the axis of rotation in this point. So any force having a line of action passing through the axis of rotation or parallel with it has no moment. So any force, its line of action parallel to the axis of rotation or cuts it, in two cases this force cannot cause rotation. So in these two cases the moment of the force is equal to 0. Why? Since in first situation, if the line of action cuts the axis of rotation, so the distance between the axis of rotation delta and the line of action of the force is null. So the moment of the force in this case is equal to 0. And if the line of action of the force is parallel to the axis of rotation, it's impossible to rotate the object or the disk around this axis of rotation. Application. Consider the figure A. We have many forces acting on the rod, on this rod represented by A, from A to C. Question: calculate the moments of the forces represented in figure A with respect to an axis perpendicular to the plane of the figure and passing through O. The positive direction of rotation is the anti-clockwise direction. So we have on this figure four forces: F1, F2, F3, F4. F1 is applied on the rod at A, F2 at O, F3 at B, and F4 at C. We have to calculate the moments of the forces represented in this figure. Firstly, if we are going to calculate the moment of F1 with respect to O, by definition the moment of F1 is equal to F1 times the lever arm, for example A1, relative to F1. This is F1. The axis of rotation, by definition or by given, is perpendicular to the plane of the figure and passing through O. So, to find A1 relative to F1, we trace the perpendicular issued from O to the line of action of the force F1. So A1, the lever arm relative to F1, is the distance OA. And if we consider F1 only acting on the rod, when we apply F1 on the rod, we show that the rod rotates in this direction, so in same direction or in positive direction chosen. So the moment of F1 is positive, and we replace F1 by its value and OA by its value, and we obtain the moment of F1. Similarly, for F2, this is F2, and this is its line of action. The axis of rotation passing through O. In this case, F2 cuts the axis of rotation, so the moment of F2 is equal to 0, since the distance between the axis of rotation and the line of action of F2 is null. For F3, this is the line of action of F3, and the axis of rotation passing through O. If we are going to find the lever arm A3 relative to F3, we need to trace the perpendicular issued from O and perpendicular to the line of action to F3. So this distance OH3 represent A3, the lever arm relative to F3. So this is the line of action of F3. Starting from O, we draw the perpendicular to the line of action. This perpendicular cuts the line of action of F3 at a point called H3. So the distance OH3 is needed to calculate the moment of F3. Now from the geometric of the figure, OH3B is a right triangle, and beta is equal on we have opposite angle, so beta equals 60. So beta in this situation equals 60 also. So OH3 is the opposite side to beta. We use sine, since sine equal opposite على hypotenuse. The opposite OH3 over OB. OB is the hypotenuse in this triangle opposite to the right angle, and we find OH3 and we calculate the moment of F3. And F3, if we apply F3 on the rod, we find that F3 makes rotation of the rod in positive direction chosen, so its moment is positive. And also we calculate of the same method F4, the moment of the force F4.